Thank you very much for having me. It's great to be here. And I'm okay. It's not okay. I'm going to tell you about some work, some recent work with Wyatt Reeves and Moshe Rosali, my collaborators at UBC. And let me start by telling you what's the context of this talk. Is it not sharp?
Intro.
So the context of the talk is conformal field theories, or certain aspects of conformal field theories. I will talk about CFTs in various dimensions, and I'm usually going to be talking about large N or large C CFTs in order for the formalism I discussed to be useful. And what I'll be doing, I'll be mostly concerned with the physics of stress tensor exchanges in conformal field theories. And I will formulate that as some effective field theory of reparametrization modes that describes certain aspects of large N CFTs that is particularly interesting and universal and relevant in the context of ADS CFT. So you might recognize that there's various applications of these things. So I will be talking about conformal blocks for quite some time, and about the shadow operator formalism, which is a way to think about to compute conformal blocks. Another immediate application is to out-of-time order correlation functions, which I'll get to, and then there's various other applications that I will mention later. So let me give you here another summary of various ideas that will play a role. And the goal of the talk is really to show some connections between all these things, and to argue that there's some framework where you can understand how all that fits together in some computational framework that's given by these reparametrization modes that I'll discuss. Okay, so here's the rough outline of my talk. I'll be telling you what I mean by reparametrization modes. First, very briefly in one dimension, and then in two dimensions, and then in higher dimensions. And then I'll get to the story about conformal blocks and the shadow operator formalism and tell you what it has to do with it, with the first part of the talk. And the third part of my talk is about a whole list of applications. I'll see how much time I have, how many of them I can talk about. All right. So I'll start with a very brief review of the one-dimensional case, which is conceptually similar to what we'll do in higher dimensions, and which is sort of the motivation to see, to take some lessons of what we've learned in the SYK model and see how these ideas generalize to higher dimensional theories in other contexts. So the SYK model is this model that you've probably all seen of n Majorana fermions, which you couple with some random Gaussian couplings. So, and the only aspect that's really going to matter here is the low energy limit of that model, in which this theory develops a conformal symmetry, which in one dimension is simply reparametrizations of time, arbitrary reparametrizations. Now, it happens that this conformal symmetry is broken both spontaneously and explicitly to a smaller group of reparametrizations parameterized by SL2R. So the explicit breaking of that symmetry is described by the Schwarzian action, which describes the low energy physics of that model. And here in the Schwarzian action, this mode f of tau shows up, which is the reparametrization mode in this context. And then one can study the kind of physics that this mode describes. And we'll see what can be understood from that mode and what can't. But the point is that there's some collective degree of freedom f of tau, which describes the physics of energy conservation in some sense. So one example for what you can understand from this action and from this reparametrization mode is the enhanced contribution to this out-of-time order correlation function. So that I'll get back to that in more detail, but see, it's just some 4-point function, and it's out-of-time order because the fermions are inserted at alternating times. And this has an exponentially growing piece, which is described by an exchange of this mode, roughly speaking. So that's one of the examples. Now there's another observation that the Schwarzian theory, the Schwarzian action, is in some sense hydrodynamic, and in the sense that it captures the energy conservation. For the experts, it's a theory of the H=2 mode in the SYK model. Or in the context of ADS CFT, if you study ADS2 gravity, it's a theory of boundary gravitons. And this hydrodynamics here, you can make that more precise, namely this action, if you write it in slightly different variables, it looks very much like a hydrodynamic action and so on. So this analogy goes pretty far. So the question has come up, for instance, in this paper, whether this Lyapunov growth of the out-of-time autocorrelator can be captured more generally using some effective field theory, some hydrodynamic-like theory of some energy mode. And in some controlled context, we will answer that question to some extent.
Felix,
Yeah.
So you mentioned that if you manipulate the action, you can actually find something that looks like hydrodynamics action. Which type of hydrodynamics would it be? Would it be like a one-dimensional type of hydro, or
yeah? So there's only one dimension.
A perfect fluid with just one variable, or
right,
because this action is only one-dimensional, right? So it's just
yeah. So it's a very simple hydrodynamics in that case.
It doesn't have like gradients.
It's just one-dimensional.
I see. Okay.
Well, there's time derivatives, but yeah, and it's a very simple fluid. There's no dissipative effects or anything, but it's also, without going into the details, the modern way to think about hydrodynamics is in terms of some sigma model, so maps from some fixed world volume space-time into some target space, or in that case, it's the physics of some world line particle, which is precisely what this reparametrization mode is, by definition. Okay. I might get back to it later. All right, that's the review about one dimensions. Now I'll talk about two dimensions, where there's a similar situation, but the physics is a bit different. It's the physics of two-dimensional conformal field theories, and I'll be interested in finite temperature situations, so 2D CFTs on the circle. And now, of course, again, there's a conformal symmetry, which in 2 dimensions I can think of as holomorphic and anti-holomorphic reparametrizations. But that again is broken. So there's a conformal anomaly, or in particular, I'll be interested in finite temperature physics. So there's some finite energy density, and I want to associate some Goldstone mode with this. I'm going to think of these reparametrization modes as some degrees of freedom whose dynamics I can study, which describe the physics of this conformal symmetry breaking. And I will argue that this is a useful way to think about it, especially at large central charge. At large central charge, you can write down a systematic theory for these modes here, which follows the rules of effective field theory, and which you can use to understand all sort of things that I'll talk about. So the claim is that thinking about these reparametrization modes provides a useful way of repackaging some universal aspects of CFTs. And they're universal in the sense that they're associated with stress tensor exchanges, with energy momentum conservation. So these are effects that you always have in any CFT. And these are also effects which may or may not be dominant if they are dominant, then they describe, so which happens, so in gravity, for instance, that's the context I have in mind, then these effects describe interesting physics related to quantum chaos, and there's a theory of the conformal blocks associated with that. So let me demonstrate how you can formulate this theory for these modes. So what we do, let's do an infinitesimal reparametrization, these z and z bars. Reparametrize them infinitesimally, where epsilon and epsilon bar are now my reparametrization modes. What such a reparametrization does is the usual thing. It sources the stress tensor. So it's like turning on sources for the holomorphic and anti-holomorphic stress tensors. So here, this is different to the case of the Schwarzian action. If I evaluate this action on conformal transformations, so transformations for which epsilon is holomorphic, so its anti-holomorphic derivative vanishes, then the action actually vanishes. So there are some associated symmetry currents, which are the usual energy momentum tensors. But more generally, I want to associate, or I want to think of these epsilon and epsilon bar as Goldstone modes, in a sense, and study their effective action. So what I have in mind is to find an effective action W like this, that I turn on these sources for stress tensors in the CFT path integral, and then I integrate out the CFT. Okay, so this may be familiar from a long time ago. This is essentially what defines the Polyakov action of 2D gravity. So Polyakov did that he sourced the stress tensor and then integrated out the CFT, and that gives you an effective action for the metric, which in generality takes this form. What we have here is in some sense a special instance of that. And also, I want to do this at finite temperature. That's maybe an important difference, at least when I'm interested in chaos and things like that. To make this analogy a bit more precise, if you take the Polyakov action, you can evaluate this is an action for some metric, and you can evaluate this 2D metric in various gauges and parametrizations. And the action that I wrote down is, roughly speaking, what you get if you parameterize the metric like this. Then you get this, it's called Alexev-Chatashvili action, which you can immediately see looks very similar to the Schwarzian action in one dimension, in the way it is nonlinear and so on. Yes?
Is it obvious that this action will be local after you integrate out the CFT? I mean, so like the one at the box looks non-local, but I guess the R's have enough derivatives probably to make it local.
So the one.
I'm just wondering about like the singularity structure.
So a priori, it's maybe not clear what you will get, but as we will see later. Well, so I claim you always get something like that. I will discuss that later in higher dimensions for the quadratic action.
Right. But this looks non-local, right? Because there are derivatives.
You're worried about the 1/box?
Yeah.
Okay. So usually that just means that the R has something like a box in front. So for instance, in this case, another gauge that you might want to pick that's very common is to say that G is just a Weil factor times a flat metric. If you evaluate this Polyakov action in that case, then you just get the Liouville action. And the 1/box cancels in a similar way.
Right. The 1/box cancels in this action. I'm just saying it's not obvious to me that the 1 derivative terms cancel in the action you're looking at when you integrate it.
Right. So
maybe that's cool.
Actually, we'll see that very explicitly at the level of the quadratic action a little bit later. Probably on the next slide already. Yeah, maybe just wait one slide. The non-locality will be very explicit. So for instance, I could write 1/box as some integral transform.
Yeah.
Then the question is, how does that localize? And we'll get to that in a second. Yeah, here it is. So if we do this at the quadratic level, for example, the quadratic action, quadratic in epsilon, I would get two integrals. So 2 sources for t and 2 t's. Because we have integrated out the CFT, these t's appear as a correlation function. So your question amounts to asking how do I get rid of one of those integrals? Right. Before I do that, let me just say that this TT 2-point function is fixed by conformal symmetry because, and that makes the dynamics of this epsilon universal. So at this point, it's still non-local, but we can already see it's going to be universal. So it's going to describe some universal aspects of the CFT. Okay, and the way it becomes local in this case. So in this case, I can integrate by parts, one of these del bar. And then I get del bar acting on the TT, the holomorphic 2-point function. Then you might think this is actually 0. But it's not quite 0 because even though TT is holomorphic, it only is away from the singularity when Z1 and Z2 approach each other. So what you actually get if you evaluate this carefully is a delta function. And that gets rid of one of the integrals. So if you go through that in more detail, you get an action that looks like this. It is now local in the sense that there's only a one integral. It is again reminiscent of the Schwarzian action. So if you replace this d bar here, this anti-holomorphic derivative, by just a time derivative, then this would be precisely the quadratic approximation to the Schwarzian in one dimension. But of course, then there's an anti-holomorphic part. And the third feature to mention is that the action is proportional to c. So this is the quadratic action. So inverting this kinetic term gives us a propagator for epsilon, which will go like 1 over c. So here you can anticipate that there will be some useful perturbation theory in 1 over c. So you can do that exercise, and you can invert this kernel and figure out what's the propagator for this mode, the 2-point function. The Euclidean 2-point function you find will look something like this. Will look like this. You can also work out directly the real-time 2-point functions. But so how should you think about this 2-point function? Well, we'll understand it in more detail later, but note it goes like 1 over c. So it's small at large c. It has a sine squared here. Remember, we're on the cylinder, so the sine squared is like what you would naively expect for a dimension -1 primary field. So this epsilon behaves like a dimension -1 primary in this sense, and then there's this log, which we'll get back to. But at this point, this is just what you get. Okay, so let me introduce some diagrammatic notation. I will sometimes just think of this is just my propagator in some Feynman diagram sense. And now we want to also couple this thing to other operators in our theory. So if we have some external probe operators, we can couple them to this mode. Because it's a reparametrization mode, it couples in some universal way by just reparametrizing the 2-point function. So doing this infinitesimal reparametrization on the 2-point function. And of course, we know from because it's a conformal field theory, we know how it transforms. This is again exactly how you would couple in the Schwarzian theory. And you can then expand the reparametrization in epsilon to any order you want. I just wrote it down here to first order in epsilon. So these green terms here, I will denote as B1 delta. So that's the natural bilinear coupling between two external operators at this reparametrization mode, which is sort of dual to stress tensor exchanges.
So primary operators.
Sorry?
O is primary.
O is some primary, yeah. So. Okay. So these are my basic Feynman rules, if you like. And at large C, so all I did here works for any C, of course, but it's only useful at large C because then you can use these things to do perturbation theory. So the first question you may ask is, so what does this compute the simplest thing you could possibly compute with this is this diagram here, where you exchange this reparametrization mode between four external operators, and you can ask, what does that compute? And the answer is, if you spend any time on the Schwarzian theory or the SYK model, you know what's the answer. The answer is it computes the stress tensor contribution, the leading stress tensor contribution to the 4-point function, which is related to the out-of-time order correlator. So that's an immediate application of that. So just in case anyone has not seen that, let me very briefly say again what that is. Usually we study these time-ordered correlation functions, which just factorize and then to very high accuracy, they just factorize into 2-point functions. But then it was noted in these papers that something interesting happens if you put the correlation, the operator insertions in some order which is not according to the Feynman path integral, but rather you introduce some multi-sheeted or some back and forth time contour. So this is a contour in the complex time plane. You go back and forth and insert operators in the past and in the future in some alternating fashion. Then this thing has an interesting behavior. It has this exponentially growing piece with some characteristic time scale of exponential growth associated with it, which is this scrambling time for the log the entropy. And the growth happens at with some Lyapunov exponent lambda, which obeys some bound, but this is the maximal Lyapunov exponent that's allowed, and the physics I've described so far saturates this bound. So the answer of what this 2-point function of bilinears computes, it computes the stress tensor contribution to the 4-point function, and if you go to analytically continue to the regime where you're in this out-of-time order configuration, it precisely computes the OTOC, this out-of-time order correlator. Or alternatively, I could have not ever done any analytic continuation and just formulate the theory of these epsilons directly in Lorentzian time. I didn't do that on the previous slides, but that would be straightforward. Okay, so that's an example of what this describes. Other questions so far? Okay.
So you see that for the reparametrization mode, you always get the maximum allowed boundary?
Yes. So this reparametrization mode was the source for the stress tensor. As we'll see in more detail, it captures the contribution of the stress tensor exchange to the 4-point function. Or in CF.
Why is it maximum coding? It's just basically for any CFT, you got it as maximum coding.
The stress tensor contribution will always be describing maximal chaos. The question is whether that contribution dominates. And that may depend on the theory. So it could be that this mode I'm describing is not the dominant contribution, but it's sort of the gravitational contribution, if you wish. All right. Now, you can do this game in higher dimensions. I've already explained in some detail how it works in 2D, so I can be more brief. If you're in even dimensions, then this statement that the divergence of t 2-point function is proportional to a delta function, then that is still true in higher dimensions. So the only difference is you have more indices now and more derivatives, but you still get some non-zero contribution, and that defines a quadratic action for this reparametrization in the same way basically as in 2 dimensions. So the quadratic action, you would just write two of these. So you have at the quadratic level, you have 2 sources for t, which are the derivatives of the reparametrization. And they source t. We've integrated out t, so what shows up is the 2-point function of t. The 2-point function of t is still universal in higher dimensions. If I were to talk about higher orders in this action, the cubic action and so on, then these would not be universal in higher dimensions. So it's a different story what to do about that. But for now, we only need this quadratic action, which is universal because it's only proportional to CT. It's the only dependence on the theory. Okay, now you can again sit down and so first use this identity to get rid of one of the integrals, and then invert the kinetic term to get the propagator for that mode. If you do that, you find this answer here. It's again proportional to 1 over CT, the normalization of the 2-point function. Then the indices come from this structure here. You could have guessed that. That's basically the structure you have to find from conformal symmetry. And then it's proportional to x squared. And again, what that means it behaves like a dimension -1 primary in some sense. Well, a dimension -1 vector. The vector indices are given by this conformal inversion tensor, and x to the power 2 tells you that it's as if it has a dimension -1. And again, this log shows up. And what's different here now, what I should have mentioned earlier, is that I'm not working at finite temperature yet. This identity is for flat space. So what I have derived here is the 2-point function for the reparametrization mode on flat space. So the log looks a bit different, and in particular, there's some scale here, some arbitrary scale mu squared, which I have to write down, which I have to put there in order for the argument of the log to make sense. This is related to the fact that there's a conformal anomaly. It's the same kind of scale that shows up when you study the conformal anomaly. And what's important is that, of course, this arbitrary scale, even though it shows up in this epsilon 2-point function, it's not going to show up in any physical quantity. So any physical correlation function I compute, this will go drop out. So to understand this relation with the conformal anomaly, you can understand this identity we had on the previous slide. This one. Imagine you want to derive this line. What you would have to do is take the 2-point function of t and regularize it in some suitable way. So for example, by doing some dimensional regularization and putting some epsilon there. And then it's just the usual story that if you do that, you end up introducing a scale. Anyway, so we can again define bilinear couplings the same way as in 1D and in 2D by just taking a 2-point function of some primary operators v and reparametrizing them. If I do an infinitesimal reparametrization, this induces this coupling. Again, in flat space. Other questions? So I'm stressing flat space, but it's actually not so crucial. But so the difference to 2 dimension is that in 2D it was basically trivial to go to the cylinder because you can just do a conformal transformation. In higher D, something similar is true. You can do a conformal transformation, but not to arbitrary space, not to arbitrary temperature. But the conformal transformation that's natural takes you from the Rindler wedge to a hyperbolic space times time. And you can now study thermal physics on this hyperbolic space, but the only price you pay is you're on a hyperbolic space. You cannot choose an arbitrary background by doing this simple conformal transformation trick. But okay, so we can, by just doing a conformal transformation, what we can do is study thermal physics, such as this Lyapunov growth in Rindler space on that background. So I'll get back to that later. But you can already imagine that it's somehow similar to the 2D case. So let me postpone that for the application section, and for now stick with the flat space case, and talk more about these rules, definement rules for my reparametrization modes in flat space and what they compute. And okay, and what this relates to is going to be conformal blocks. So this is going to provide a useful language to understand conformal blocks at large central charge. Okay, so okay, here's another bit of review. What is a conformal block? Consider the operator product expansion in some Euclidean conformal field theory. So you can expand these 2-point functions, have in mind the same kind of two operators that gave rise to the natural bilinear operators we had before. You can expand those in terms of sums over primaries and their conformal descendants. I'm sometimes going to refer to this as the OPE block, which may not be a very well-defined object, but let me call it that anyway. So by the OPE block, I will just mean this contribution to the OPE from one conformal primary and all its descendants. So here's an object that's more well-defined. If I take a 4-point function and I OPE the operators pairwise, so I do this OPE twice, and I expand in the same, so then in some OPE channel, the contribution to this 4-point function is the conformal block. And the diagram I'm going to draw associated with this looks like that. And this conformal block is, again, a purely kinematical object in the sense that it only depends on conformal cross ratios and operator dimensions. But it does not depend on the details of the theory, such as these OPE coefficients. And so in some sense, the conformal block is a 2-point function of this OPE block thing. Now, how do you compute these conformal blocks? So there's of course a lot of literature on that. I'll only be concerned with very simple cases. But roughly speaking, one way to compute the conformal blocks is by solving this Casimir equation. So if you act on these blocks with the conformal Casimir, because they're just purely kinematic objects, they're eigenfunctions of the conformal Casimir, and the eigenvalue is determined just by these data, the dimension and the spin of the operator that runs in the OPE. But now you'll notice that this eigenvalue is invariant under sending delta to d minus delta. All right, so there's another conformal block which has dimension d minus delta, which has precisely the same eigenvalue. And I'll refer to that as the shadow block. So it's like the conformal block associated with some shadow operator, which is the operator which has this dimension delta tilde equals to d minus delta. So the Casimir cannot distinguish them. The way you can distinguish them, the physical and the shadow block, is by looking at their short distance behavior, or their monodromy around the point, the singularity, where the points become coincident. So if you do that, you'll see that the physical block, okay, in terms of the cross ratios u and v, the short distance limit corresponds to u going to 0 and v going to 1. So you want the leading term in that expansion. And then you'll see that the dependence on u is different for the block and for the shadow block. So this short distance monodromy distinguishes them. So, okay. So that's how you distinguish them, which means if the thing you want to compute is the physical block, meaning the contribution of some primary you pick to the OPE, or to the 4-point function, then what you have to do is somehow project out everything that has this monodromy, the wrong monodromy. So there's a monodromy projection you have to do. Okay, but let me say a little bit more about these shadow operators, because they're a useful concept to do calculations with. So as I said, the shadow block is like the conformal block associated with the exchange of some shadow operator O tilde, which has dimension d minus delta. Now this operator may not actually exist because it has a weird dimension, but I can nevertheless define some formal object. I can define it this way, and that's actually going to be a useful definition. So, okay, this definition may seem like a non-definition, but on the right-hand side, this two-point function of O tilde, by that I just mean the two-point function of some primary, which is fixed by conformal symmetry, has a universal form, that I would get if there was a primary with this dimension. Okay, so this is just the conformally covariant two-point function. And in terms of that, I can define what I mean by this operator O tilde.
Why not exist?
Huh?
If you define it this way, why does it not exist? It doesn't just show up in the
I mean, it has this dimension, which is usually not physical. It's
if you define it this way, why would it not exist?
Well, okay, so the way I defined it here, it's defined in terms of O, but it's non-local. So there's some non-local definition in terms of O. Yeah, in that sense it exists. Okay, now why is it useful to define that? So once I have that, I can define this projector, and that's really the useful object. This is supposed to be a projector onto the conformal family of O, so exchanges of O and descendants of O. I claim that inserting this projector in a four-point function does precisely that. It projects you onto exchanges of O and its descendants. And this projector is defined in terms of that object. So I can do that now because O tilde times O has dimension d. So I can define a dimension 0 projector this way. So let's see. So unfortunately, this is not quite true. If you actually insert this projector in a four-point function, you don't get the block associated with the exchange of a dimension delta. But what you get is a combination of that block and the shadow block, this object that the Casimir was not able to distinguish. Okay, so this projector does something good. It projects us onto the conformal family of O, but it contaminates the result by the shadow block. So I'll refer to this linear combination as the conformal partial wave. So if you compute the conformal block using this technology, then at the end you'll have to project out this piece. You have to do this projection onto the piece which has the right monodromy. But that's okay. So we can handle that. But we have now made the calculation much simpler, because if you explicitly do that and insert this projector here, then you reduce the problem of computing the right-hand side to some integral, and then there's two three-point functions. Okay, so you have to do some conformal integral over three-point functions, which is a doable task, but we'll simplify it further. So now these OPE blocks that I mentioned in the beginning, we can understand them from this perspective. So if you don't take the full four-point function, but you just take two operators, say you OPE these two operators, and you just act on that with this projector. You can ask what happens if you do that. And you can calculate that very explicitly. You can plug in the definition, and you get some integral. And the kernel of this integral is the three-point function with the shadow operator. So this three-point function is again fixed by conformal symmetry. So you get some universal integral over O, the guy that we want to OPE into. the result will be proportional to the 2-point function, so I'll factor that out, but then you get some universal kinematical object BO, which is precisely, oh, nothing else, which is precisely this OPE block I defined in the beginning. Right? Does that make sense? I'm getting too confusing. It's maybe a lot of stuff if you're not familiar with this. So the point is that I want to argue this OPE block is somehow a natural object in this theory. It's the universal kinematical part that you get if you OPE two operators into O and descendants. And one way to describe this OPE block is by just taking the OPE of these two operators and acting on it with this shadow projector. And then you get an explicit expression for this OPE block as an integral against some 3-point function and O. So it's an operator. This goes like O, and there's an integral transform of that operator. Now let's talk about the stress tensor block. So far this was about arbitrary primaries that you exchange here. Now let's focus on the case where you exchange stress tensors and descendants. So in that case, there's a special feature. So I defined for you before what I mean by O tilde. Now let's look at T tilde, the shadow of the stress tensor. As we had it before, this was defined as some integral transform with some universal kernel against T. And in the case of the stress tensor, you can actually write this whole thing as a total derivative modulo some symmetric traceless projection. So there's some explicit expression here, but it doesn't matter. The point is just you can write the shadow of the stress tensor as a total derivative. And that means there's more games you can play with this. In particular, we know the 2-point function of T tilde. It's just given in terms of the 2-point function of T, so you can write down some expression for it. And the 2-point function of this curly E here follows, right? Because it's just the object that I have to take two derivatives of to get the 2-point function of T tilde. So you can compute what that is, and you'll find this expression, which is precisely what we had before from thinking about the reparametrization modes. Right. So we find precisely the same 2-point function for the reparametrization modes as for this curly E, which is the object whose descendant, in some sense, is the shadow of the stress tensor. Okay, so this is the connection between the two topics I've been talking about so far. And by dimensional analysis, that makes sense, right? We already saw this is dimension -1 vector, and so is this, because its derivative is a source for T. Now, but let's check this in a little more detail at the level of the bilinear couplings. I already told you about the bilinear couplings in both of these stories. So the bilinear coupling that was natural from the point of view of these reparametrization modes was just a reparametrized 2-point function expanded to linear order. The bilinear coupling that was natural from this shadow operator story was the OPE block associated with stress tensor exchanges. And the OPE block, as we saw, can be written explicitly as an integral some integral over T with some kernel that's fixed by the dimensions. So these two objects should also be the same, if this makes sense. And that's indeed true. So you can, for example, you can calculate the 2-point function of these guys. In the beginning, I already told you about the 2-point function of that guy. If you want to do the 2-point function of that guy, of this OPE block, you have to do 2 conformal integrals. So that's a bit more work. So we can see here, okay, I have it explicitly. So if I want to compute the stress tensor contribution to some 4-point function, I can do that using this OPE block. by OPEing VV and WW into T. And that is described by these OPE blocks, each of which is a conformal integral. So if you calculate this way, you have to do 2 conformal integrals over a GT 2-point function. But of course, using these reparametrization modes, that was much simpler. So we didn't have to do any conformal integrals. We just had to compute this Feynman type diagram, which simply involved a propagator of that mode, which we already determined. So it's a different perspective on how you think about the OPE and these OPE blocks. Okay. And indeed, if you do that, if you use the reparametrization mode technique, you can actually compute this in this 2-point function or the stress tensor contribution to the 4-point function in any dimension, and you get some closed form expression. In 2, 4, and 6 dimension, Dolan and Osborne wrote down very complicated and very general expressions for that. And they, at least in the dimensions where they could do it, this matches this very simple expression. Right. I would go to applications now, unless there's questions.
Is the operator well defined for the odd-time number? From the shadow operator?
Yeah, this is confusing. So the effective action approach in the beginning only gives you something non-zero, a non-zero action in even dimensions, where we had this anomalous behavior of the TT 2-point function. The shadow operator formalism doesn't really care about the number of dimensions, as far as I know. So there seems to be some tension. So also this result here. So using this reparametrization mode techniques, I can get this in even dimensions. Question is what happens in odd dimensions. Yeah, I don't know. So the reparametrization mode story, the way I thought about it, doesn't work in odd dimensions. And this should be related to the fact that these conformal blocks are very complicated in odd dimensions. So in odd dimensions, I would not expect a simple expression like that. But these blocks are typically some horrible integrals that you can't do explicitly, and it's much more complicated.
Can you do just working from the shadow operator thing to guess what's the expected form and effective action?
Right, so naively, the shadow operator thing would tell you that the 2-point function of epsilon should be the same in any dimension. So you could ask whether you can get that from an effective action in odd dimensions. Right, I haven't actually tried to do that. Yeah, but maybe that should work. I don't know. As far as I know, there's no problem with the shadow operator formalism in odd dimensions. But I may be. Yeah, I don't think so. Okay, so here's a number of applications that I could talk about, but probably won't have time. So, okay, yeah, let me just get started. So this is what I already mentioned before, that we can, in this higher dimensional setup, I've been discussing flat space physics. Now it's interesting to study thermal physics. And the most immediate thing you can do is do this conformal transformation to hyperbolic space. And that allows you to study the OTOC on hyperbolic space. If you compute the 2-point function of the bilinears, so the stress tensor contribution to the OTOC, again you run into this issue that you get the physical block plus the shadow block. You do this monodromy projection, this thing that tells you that one of the blocks has the wrong short distance behavior, so you project that out. You're left with the physical block, and you can do the conformal transformation on that one. And then you just find thermal physics, thermal OTOCs from this block. And what you find is a result that's already been known for some time. What you find is that this 4-point function has the Lyapunov growth with maximal exponent, and the butterfly velocity, which determines the dependence on this distance, which is some notion of hyperbolic space invariant geodesic distance in this case goes like 1 over dimension minus 1. Okay, here's another application. You can study higher point out of time order correlators. So we have learned that these 4-point OTOCs are interesting. They capture some physics that usual Feynman path integral does not capture. So you can ask what happens if I put more insertions and if I go more and more out of time order. So I go back and forth in time multiple times. Now, as you do that, there's more and more possible configurations you could study, and some of them are easier and others are harder to study. We found that this configuration is particularly nice to study and also displays the feature that we want to see in the maximally in the maximal possible way. The feature I'll describe in a second. So some of this is a very good observable if you want to study higher point OTOCs. We have pairs of operators, and they're sort of chained together in the Euclidean time direction, and they progress further and further in the real time direction. So if you want to compute this, the computation is very simple using these reparametrization modes. You simply replace each pair of operators by one of those bilinears, and you exchange reparametrization modes between them pairwise, or in some chain. That gives you the leading contribution at large C to this observable, and what you find is that it behaves like this. So the growth in time is with the same Lyapunov exponent as before, 2 pi over beta. But the scrambling time, so the suppression of this object in 1 over n, is higher. So the whole thing goes like 1 over n to the k minus 1, which is saying that the scrambling time, this time of order log n, has gone up by a factor of k minus 1. And each of these statements separately doesn't tell you much, but both of them together are interesting because they tell you that the characteristic time scale, so the ratio of these two coefficients between the time and the scrambling time, actually depends on how many insertions you have, and it grows. So there's some hierarchy of time scales that grow longer and longer the more insertions you put. So these higher point OTOCs actually tell you something that encode some more fine-grained physics that the 4-point OTOC did not tell you. And that's easy to compute using these methods. Okay. Clear? Then here's another application which goes by the name of pole skipping. So this is proposal in these papers from 2 years ago or last year that some of the features of what I described are actually more general in chaotic theories. That I described the theory of the reparametrization mode as encoding the physics of stress tensor exchanges. And what they argued is that you can see these features of chaos that characterize the chaos already in the 2-point function of t. Now, from the story I told you, this is not very surprising because everything came from the 2-point function of t. That was the thing that determined the epsilon 2-point function. But there was a different characterization here that was described here, which is that this tt 2-point function has some rational function. It has some poles and zeros. Well, it doesn't have to be. It has poles and zeros. The poles you can think of some continuation to high frequencies of the hydrodynamic diffusion pole. But then there also occur zeros in this 2-point function. They usually occur when omega is of order t. And the observation was that the poles on the zeros, they sometimes collide. So the pole is skipped. The pole is just not there at some special points. The proposal was that this happens at these special values of frequency and momentum, when frequency is the Lyapunov exponent and momentum is the butterfly velocity. So by finding the point of this pole skipping, you can already see from the tt 2-point function what these values are. Okay, in this context of CFTs that I was talking about, you can observe that explicitly and you can understand why it happens. So in a 2D CFT, the TT two-point function momentum space looks like this. And it has this feature that there are poles at omega equals k. And if you analytically continue to complex frequencies and momenta, this pole is skipped when omega is I or minus I, which is the value of the Lyapunov exponent times I. And the reason this happened was, very schematically, because epsilon two-point function from this effective action was like 1 over the two-point function of t, very schematically. So if epsilon grows exponentially, so we have this chaotic behavior, it means that in frequency space, this TT better have some singularity at the point where that determines the exponential growth. Okay, so you can study that in 2D CFTs. You can study that in higher DT CFTs, where the two-point function of t looks much more complicated. So we computed that, and yeah, it's more complicated, but you can get an answer, and the answer, interestingly, involves so there's two parts to it. There's this polynomial prefactor, which gives you some zeros. It gives you zeros when k takes certain values, like I times d over 2, I times d minus 2 over 2. And then you get various poles from these gamma functions. Okay, so you can look at that for a long time, but you can also just plot it, and then it looks like this. These blue lines are these cold lines. They are the poles of those gamma functions, and the warm lines are zeros. And the interesting one, so here is in the middle is frequency 0. So chaotic behavior has to do with zeros in the upper half omega plane. Anything that happens in the lower half plane leads to exponential decay instead of growth. That's not interesting. So the points where the zeros and the poles collide are precisely at the value of the Lyapunov exponent and the butterfly velocity. So that's a nice check. Okay, I'm out of time. So here's something more recent. Trying to understand. Okay, I'll be brief, so you may lose me here, but it's interesting to understand these conformal blocks in certain regimes. In particular, the regime where two operators are heavy and two of them are light, because this is like having two probe operators in a black hole background. So the quantum corrections to that and so on are very interesting and encode lots of interesting physics. And you can try to understand that from the point of view of these reparametrization modes. So in particular, the heavy, light Virasoro block in 2 dimensions is known in closed form. And it depends on, So it depends on the dimension of the light operator and the dimension of the heavy operator, delta heavy, which we take to be of order C. So this parameter mu is of order 1. So this is known in closed form as a function of this alpha, this ratio of delta heavy by C, and delta light. You can try to understand this order by order in these two parameters, mu and delta light, by figuring out what Feynman diagrams in this reparametrization mode language these contributions correspond to. And why is that useful? Because it's useful because you can write exactly the same diagrams in higher dimensions. And that is still an open problem. So there's been some recent progress. But it's still an open problem to understand fully the heavy, light block in higher dimensions, which encodes interesting things about black holes. And an idea is that, because these calculations are almost identical in higher dimensions, so maybe that's a useful approach. So for instance, something people try to show is that this exponentiates also in higher dimensions under certain assumptions. Okay. Submaximal chaos, ask me about that if you're interested. And then there's some more insights about the monodromy projection and the shadow operator formalism, which are a bit technical, so I'll skip that as well. It's basically about the gauge you choose for the Polyakov action. And I'm done. Okay, here I'll leave you with this summary. I've described some systematic effective field theory for these reparametrization modes, and they offer a new perspective on OPE blocks and natural operators in this bilocal in this space of bilocal operators that couple to these reparametrization modes. And there was a very close connection between the reparametrization modes and the shadows, which explains why the reparametrization modes are useful for computing conformal blocks and provide you a different formalism to get the stress tensor contributions. And here were some of the ideas for future work. Thank you.